So section 4.3 is about multiplying polynomials. In 4.1 we simplified, added, and subtracted polynomials. Let's look at that's why it's moving. It's all right. So if you have two binomials, okay, if you have two binomials, you've been taught FOIL, right? Have you heard the word FOIL before? First, outer, inner, last, which is fine. So that's why I write at the start. But FOIL is just another way of saying what's called double distributive. Or another thing, have you heard of box method before? Anybody use box method to multiply? It's a good way of organizing in like a table format. So I'll show you both ways. You can choose which way you want to use. All right, but again, I don't usually remember the word FOIL. I usually think of it as double distributive. For example, here. Simple, right? You can FOIL this out, come out with the result. Now, instead of remembering FOIL, just think about it this way. Distribute the first term to both, like that. And then the double distributive part comes about because you then distribute this to both. Okay, so when you have a sum or a difference, you're going to distribute both terms in the sum or difference to both terms in the other binomial. Okay, so we take both of those and distribute them equally. So the x goes to both and the 2 gets distributed to both. But again, you can remember the word FOIL, but it doesn't really matter. The minute you have a trinomial instead of a binomial, the word FOIL doesn't make sense. So you just think about double or triple distributive method. All right, so let's take a look at this. If the current function, all right, current I of t is represented by the following, and R of t represents the resistance function, then find what's called the voltage using Ohm's law, V equals IR. So in an electric circuit, the voltage that a circuit has across its plates, or its terminals, I guess you should say, is really equal to the current times the resistance in the circuit. So if we have a current function I of t and a resistance function R of t, then come up with the voltage function itself. And then find out the voltage at 2 seconds. Okay, then find the voltage at 2 seconds. So if I wanted to find the current at 2 seconds, how would I figure that out? Think about functions, when we did functions in section 3.9. Okay, I want to find out what the current is, I, when the time is equal to 2 seconds. So how am I going to figure that part out? Remember, this is the definition of I of t. And I want to know when time equals 2 seconds, what is the actual current in amps? What is the actual current? What do I do for this kind of a problem, Sabine? Yeah. Again, remember how we did like f of x equals g of x equals, and we said like, all right, f of 2. How do you do f of 2? You take a 2 and you plug it in everywhere. So here we're looking at the current when time equals 2 seconds. It says it right here, 2 seconds. So a 2 goes in for time. So you plug a 2 in there. You plug a 2 in right there. Okay, and then you subtract that 6 off. So what do you get as an answer for current at 2 seconds? What do you got? 10? Check again. 18. Right? This is 2 times 8 plus 8 minus 6. 16 plus 8 minus 6 is 24 minus 6. You did 2 times 2 to the second. That's what I can tell you. You raised this to the second and made that a 4. Yeah. All right, so the current is 18 amps after 2 seconds after the circuit has been open or closed for 2 seconds. Now, we then want to find out what the resistance is. Find out the resistance at 2 seconds. So do the same thing for resistance now. All right, now plug in a 2 for T. Oops. That's cube, that should be square. So we're going to 8. Looks like minus 8 minus 5. What are you going to get as a result? Negative 5. Okay, which I should change these numbers for next year. You shouldn't get a negative resistance. A negative resistance would mean it actually helps the electrons flow. Okay, so hypothetically speaking, those are our two answers. Now, we want to figure out what the voltage is at 2 seconds. And we're told the following. We're told that voltage is equal to current times resistance. So I could just multiply those two numbers. I could say, well, the answer I got was 18 for current. Resistance was negative 5. That gives me negative 90. And that could be my voltage. But let's go ahead and figure out the voltages in terms of a function. Let's figure out what the voltage function is. Let's go back and do this part right here. All right, we'll figure out what the voltage function is. So if the voltage is defined as the current times the resistance, take those functions and multiply them by each other. So you need to take this up here and multiply it by this down here. So it's no longer a binomial times a binomial. It's a trinomial times a trinomial. Right? 2, 4, negative 6. So it's this times this. All right, so we're multiplying those two things. This is the current function. This is the resistance function. Current times resistance is what voltage is. So that's why we're doing this, to figure out what the voltage function is. Now, I'm going to go through two methods to do this. You can choose whichever way you'd like to do it. Doesn't matter. First method, I'll use what's called distributive, or in this case, triple distributive. I need to distribute this 2t cubed to all three of these. So 2t cubed times t cubed. What does that give me? Remember your rules, please. No. See, there's your rules. Guys, you tell me that you get the rules and you're missing your rules. Multiplying two things with the same base. What do you have to do to the exponents? Add the exponents. Okay, the 2 is just a coefficient. It's a multiplier. So this 2 remains. T cubed times t cubed is t to the 6th. Next, 2t cubed times negative 2t to the 2nd. 2 times negative 2. Do that part first. What do you get from that? Negative 4. Then t cubed times t to the 2nd. T to the 5th. Then take 2t cubed times negative 5. Just multiply the coefficients. Just multiply the coefficients. Negative 10 t cubed. Okay, don't forget the t cubed from here. All right, that's what I get from that first distributive. I don't know why I changed that to blue. It should all be red. Okay, so that's what I get from that result. Now, I then have to go ahead and do this. Distribute 4t to all three of these. So you have to do this next. 4t times t cubed. Ben, what do I get? 4t times t cubed. 4t to the 4th. Very good. 4t times negative 2t squared. 4t times negative 2t squared. Very good. And then 4t times negative 5, Niall. Negative 20t. And we're almost done. Now we have to take the negative 6 and distribute it to all three. Giving us simply negative 6t to the 3rd plus 12t squared plus 30. Now you've got all these terms. It's all one line. I just went over the next line. Paul, what do I have to do now to make this look nicer? Yeah, so anything that goes with a 2t to the 6th anywhere? No. How about t to the 5th? No. How about t to the 4th? No, there's only one of them right here. Looks like there's only one of them still, right? T to the 3rd, yes. Yeah, absolutely. What do you got for t to the 3rd, Charles?
Negative 16.
Yes, negative 10, good. Negative 8 is negative 18. And then where's the other part?
And there's a negative 60 there.
So negative negative 24. T to the third. All right, then t squared. I've only got one of them by itself, it looks like, right? Right here. Then t linear. Where's the linear t? Remember, linear means to the first power. Yeah, negative 20t. And then the only constant that's left is this 30. So this is my answer for the voltage function. What's the degree of this polynomial? What is the degree of it? Nina? 6. 6. Because remember, the degree is the highest degree of any of the monomials. This is clearly the highest. There are no other variables to make it any different. So that's my result. Now, do me a favor and plug in 2. Find the voltage when time equals 2 in this one. It might be a little bit messy, but work with it. By messy, I just mean some math. I'm running out of room, so I'm going to the next. You either check on your calculator to make sure you're doing it right. Write out each line like I'm doing here. Okay, the 128s clearly cancel. I'm not going to add those, doesn't make sense. And I've got 64 and 48 is going to give me 112. And 30 is going to give me 142 as a positive. Then I have a negative 40. And a negative 192 is negative 232, yielding negative 90. Okay, exactly what we had expected. Why do we expect that it comes out to be negative 90? We expect that because earlier we got a current of 18 and a resistance of negative 5, and 18 times negative 5 is negative 90. So if we evaluated the current and the resistance and then multiplied them, it's the same answer that we get as if we just evaluate the voltage function itself. Again, this is just because of Ohm's law. I'm not asking you, you're not going to be asked on a test about Ohm's law. But if I give you a relationship, if I say to you that, I don't know, F equals ma, Newton's law, have you heard that before? F equals ma. If I say the mass of a rocket changes as a function of time because it's burning rocket fuel, which is what happens to the rocket. It burns its rocket fuel, so its mass decreases. So the mass changes as a function of time, and the acceleration changes as a function of time. Determine the force, F, as a function of time. You have to take the mass function times the acceleration function, multiply those functions together, giving you the force function, like you got the voltage function here, and then plug in what you're looking for. Okay? Let's pause there for today. In example 2, we're given the function h of x, we're given the function g of x, and the function u of x. Then we're asked to find the quantities 2 times g of x times u of x, h of x times u of x, and then h of x times g of x times u of x. So, part A. What is part A asking me to do? How can I start part A? What's 2 times g of x times u of x mean I have to do? Go ahead, Will.
Plug in the formulas for gx and ux.
All right, so go ahead, give me g of x.
G of x is negative 3 times x to the second power plus 4x minus 2.
All right. And then u of x, go ahead.
4x plus 2.
So if you're looking for the product of two functions, you're literally just going to be multiplying those functions as seen above. Now, let's talk about test strategies, because I feel like some people don't always take the path of least resistance. If you want to travel between 2 points, the best path is a direct line. Well, a problem like this, you're making it more difficult if you double everything first, because then you're just making the numbers bigger, and then you have to multiply. So multiply your trinomial times your binomial first, then just double everything in your answer. You follow what I'm saying? Choose the route that makes the most sense. Don't pick a method that makes you do more work at the end of the problem as a result. So let's multiply. Now, yesterday I showed you double and triple distributive, right? Where you distributed each term. You took 3x squared, distributed, 3x squared, distributed, then 4x, then negative 2, and then it was a negative there. So what I want to do today is box method for this example. So you can see how they're the same thing, but box method is like an organizational grid. So take a look at your terms. You have a trinomial and you have a binomial. So make a box that has 3 rows and 2 columns, or 3 columns and 2 rows. It doesn't really matter. Okay, 3 by 2 because it's a trinomial and a binomial. Along the 3 columns, I'm going to put the trinomial terms. All right, so I'm going to put the 3 terms where I have 3. If you made 3 rows and only 2 columns, you're going to put your 3 terms along the left. It doesn't matter, it's the same. And along the part where there are 2 rows, let's put 4x plus 2. And please write down the signs, or at least make sure you write down the negative signs at the minimum. If you don't write down a sign, like 4x, then have a sign next to it so you can write it. Okay, so if you want to erase the positive signs, that's fine, but don't forget your negative signs. And now at this point, just use the multiplication method, looking at each grid location, lining them up. Okay? And at the end of the day, you're going to get 6 results. If you had triple distributed to a binomial, you would get 1, 2, 3, 4, 5, 6. You get 6 results. So it's identical to the double or triple distributive method. For example, 1, 2, 3, 4, and then 5, 6. All right, it's the exact same thing you get. So go ahead and multiply corresponding spots and fill in those boxes. Check your answers, please, as you go along. Please try this by yourself, though. Make sure your rules are down pat. If you get one wrong, try and figure out why it's wrong. If you can't, then ask. If I made a mistake, let me know. I think those are good. Take a look and check, make sure your answers are good. At this point in time, what are you going to do? What are you going to do next? Yeah, these are all your terms. Just combine like terms. Now, if you write them in the correct order of decreasing degree, you'll notice that the like terms are diagonally lined up. This will always happen if you use decreasing degree. You'll get that diagonal line up. You see that? Okay, so the x squared, the x squared, the x and the x, the cubic, and then the constant. So you'll pick up on that pattern. It makes it easier to combine. So we've got negative 12x cubed. How many x squareds do we have?
We have 10.
10x squareds. Because we have 16 minus 6, really. How many x's do we have? 0. None. So there's right minus 4. Now, this is my intermediate answer. What do I have to do still? There's one more step. I had you ignore it earlier.
Multiply everything by 2.
Yeah, don't forget about this 2 up here. So this was the result of this operation of multiplication. But we have to double everything. Okay, that's our final answer there. Now, there's a tendency for students to try and factor stuff out when they're evaluating or simplifying. There's no need to factor anything out here. You could have just put the 2 out in front. It's clearly everything is divisible by 2, but it's also everything is divisible by 4. Yeah, good, Nina. 4. So you can bring a 4 out in front, but honestly, unless you're solving an equation, there's no need to factor stuff out of your final simplification. Does that make sense? Because you know what happens? I get students, because later on when we solve equations, you're going to like set this equal to 0, find the factors, factor out a constant, ignore the constant. So people factor out like a 4 here, and then they drop it off as if it disappeared, because they think of it as equal to 0, or you can then just divide by 4. So you can't just divide everything by 4 suddenly. You could write it factor out if you want to, but don't ignore the 4. It's got to be out front. All right? There's no real necessity though here. Can you try part B on your own? Try part B on your own. This should be very simple. So what method might you be using for this? When people choose? Did you choose box or did you choose?
Choose grid.
You choose grid? Okay.
I did box.
Would you box or grid? Okay.
What is W double distributed?
Double distributive?
Distributed.
Well, box. So box, 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 double, double. I'm just curious.
Box.
Box, box.
Box.
Okay. Foil, double distributive. Good. Foil. Foil. Double distributive. Okay. So like half and half. See, it's interesting to look at that. Some years more students prefer box, so I try to get an idea. So, yeah, I mean, in this kind of problem, box is easy. It's a 2 by 2 box, or even double distributive is just foil. So when you foil, make sure you do the math in your head if you're going to foil. And here's what I mean. So there's no need to write out every step when you're foiling. So if I'm doing first, I know that it's this. Then outer, I do outer and I keep track of it. Outer gives me positive 4. Inner gives me negative 12. So negative 12 and positive 4 is negative 8. So I don't actually perform that middle step there. All right, so do outer and inner together as one step. And then the negative 3 times the 2 gives you the negative 6. Okay? Any questions on this one? Pretty easy stuff still? Right? Okay, good. The last one, we're going to multiply them all. You want to start us off with a hint here?
Well, I used from B. I used the answer from B.
Awesome, Ryan. And I was hoping people would pick up on that. Can you explain why and what you mean by that?
Well, because H and U, so it's easier. You can do a box instead of trying to figure out how to make a linear box.
Yeah. Look, this is H times U times G, isn't it? And don't you already have H times U? Right, you have H times U right here. So take that answer you got from part B and just multiply it by G. Because again, you already have H times U in this part. So take this quantity, this trinomial, times this trinomial. I would definitely use box with a 3 by 3. It just makes life easier. You can use triple distributive, but you're going to get 9 terms, don't forget. So take G of X times this answer from B. Again, look diagonally, please. Okay, look diagonally for your late turns. Just make life easier. You notice it right away. So if you know your rules of exponents, this topic is actually really simple because you're just multiplying monomials by each other, really. You're breaking down a polynomial into many little monomials. All right, what do you get as your answer?
Negative 24x to the fourth plus 56x to the third minus 30x to the second minus 8x plus 12.
What was the
30x.
30x to the second? Good. Any questions on this one? People still working, finishing up? Better, I guess. I want to take a look now at two what we call special cases, and you've seen these before, but the way they multiply when we're looking at binomials, when they multiply they come out to answers that are recurring themes or have recurring patterns to them, so it makes it easier on us. All right, so let's take a look at these rules. And we're going to look at some general cases here, and then some examples of them. So, first off, the first general rule, honestly, I didn't use when I was in high school, and it's not, I don't think, as important as the second rule. The first rule just tells you the pattern, that if you're squaring, right, if you're squaring a binomial, that you're really foiling it. So if you're really doing this, this is really a plus or minus b times a plus or minus b. The reason I emphasize this rule here is because I can't tell you how many people just square a and square b. They distribute the squared. That is not true. Again, we learned this rule a little while ago. We learned this. And that is definitely true. All right? That was the rule that we learned yesterday, was it? With the 2 days ago, the exponents? Yeah, right, 2 days ago. Now, that does not translate over to addition. If you have addition, you can't distribute the squared to each. When you have addition there, it's like you're saying a plus or minus b times a plus or minus b. You have to FOIL or double distribute or box it. And what you'll notice though, what's interesting is that when you do it, you get a squared plus, I'm going to use the plus, okay? Imagine there wasn't a minus here, just because it gets messy. Plus ab plus ab plus b squared. So you get that same middle term twice, which is what you're seeing in the rule there. So you get a squared plus or minus, depending on what it was, okay? Double ab, because you have two of these. And then even if b is negative, you're squaring it, so this is always going to be positive. All right, so look at these examples on the right. 2x plus 5y, and that quantity squared. You could FOIL it out, or you could just square the first term. 2x is 4x squared. 5y squared is 25y squared. And then, see the middle two terms? Multiply them by each other. So multiply the 2x times the 5y, and then double it. You'll get 20xy. So if you want to use that, you can. It's not as important. It's more helpful when you're trying to factor. All right, when you're trying to factor. But again, multiply these two. That gives you the AB portion right there. And then double it. And that's where you get 20xy. To get the first term, just square this whole thing. To get the last term, just square this whole thing. That's what these parts of the rule are telling you. So again, the first rule is useful But again, you could always just FOIL that. The second rule is very important because it's going to help you to factor later on. What is the second rule called? Anybody have a name for that? Did you learn about this rule with an acronym as a name? Maybe in your earlier algebra class? Starts with the word difference.
It's not like difference in sums, but it's not so.
Close. The word is not sums, but it is an S. Difference of squares, right? Difference of two squares or difference of two perfect squares. Some people say difference of two squares, dots. That's when I was a kid, my teacher said, oh, remember dots. Whenever these things are squares and there's a difference, meaning a minus sign, you can use the idea that it's a plus b, a minus b. So starting with this one here, x squared minus 16. There's a difference here, right? A minus sign. X squared is a perfect square. 16 is a perfect square, like 16, 25, 36, any of those. So it turns out that this comes about from x plus 4, x minus 4. Why is that? Why is that? What's happening when you multiply two things like this right here? When you multiply them, what do you get? There's something about it when you multiply it out. I'm not showing the work obviously here, but show me the work. What do you get? Multiply a plus b times a minus b. Somebody tell me, what do you get when you distribute it? Give me all the terms. Nina?
You get a squared minus ab plus ab minus b squared.
And what happens to those middle terms, Nina? So that's the key here. The middle terms always cancel when you multiply two things that are binomial conjugates. Let's write that word down. I'll jot it down up here. These two things, they're both binomials. One is positive, one is negative. So we call things that have a positive or a negative conjugates. So these are binomial for the two terms, right? A is one term, B is the second term. And they're conjugates because one is positive and one is negative. All right? So binomial conjugates. When you multiply binomial conjugates, the inner terms cancel, leaving behind only the outer terms. A squared minus b squared. All right, so if you had something like, let's take a look at this second one here. This is a binomial. This is the binomial conjugate of this one. So therefore I can just say, all right, the first term is u squared times u squared is u to the fourth. I don't have to do the outer and the inner part of FOIL because the middle terms are going to cancel for sure. For the outer part, I'm going to get negative 4u squared. For the inner part, I'm going to get positive 4u squared. Those cancel, so I don't care about them. So the last terms I multiply are 4 times negative 4, giving me the negative 16. It's more useful for something like this last one, right? You don't want to have to multiply those middle terms or get those middle terms and add them because you have fractions. So 3 halves k times 3 halves k. 3 times 3 is 9. 2 times 2 is 4. K times k is k squared. Oops. And I made a clear typo. Then I go ahead and I look at the last part. I'm going to say 2j cubed times 2j cubed. 2 times 2 is 4. J cubed times j cubed is j to the 6th. It's a positive here and a negative here, so I get a negative as a result. This rule will become more useful in the next section when we have to factor. When you go from something like this back to something like these two binomial conjugates. All right, practice one on your own. Okay, practice one of these on your own, please. Let's do so they're binomial conjugates of one another. Remember, the first term is not changing. Notice this negative 3x squared is still negative 3x squared. It's the second term whose sign changes for binomial conjugates, right? Or at least just one of the terms, but not both. Not both. Okay? So you can FOIL this if you want, or you can try to apply the rule. Okay, apply the rule where you're squaring the first term and you're just squaring the second term. Try it both ways if you'd like. Just check that you're right.
Nine x to the fourth power minus 1/25 using the sixth power.
Good. Very good. So either double distribute or FOIL or use the rule. So you square this first term, this right here. You start by squaring this. What's the square of -3 though? Isn't it positive? So you're always going to get a positive answer to start for this. So when you square -3, you get 9. When you square x squared, remember x squared, you multiply these powers. Okay, although when you add them, you get the same answer because 2 times 2 equals 2 plus 2. Okay, that's just a coincidence. Then we have negative, and then the 1/5 part. This portion is really squared, so 1/25. And then u cubed squared is u to the 6th. All right? So, again, you can double distribute, it's fine. It just takes more time. So if you're the kind of student who's been struggling to get through every problem on the test and have time to still check, then these kind of rules will be very useful for sure to help you save some time. And in the next section, when we factor, you're going to need to know this rule. You're going to have to be able to do this. Given just this, come up with these two. So go backwards. All right, so again, if you're given this expression and it says factor the following, you need to recognize this is a perfect square, 9. 1 is a perfect square, 25 is a perfect square. It's a difference, clearly. Any variable to an even power is always a perfect square because you can just divide that power by 2 to get what you get as a result up here. Is that what you're going to ask about the powers?
I was going to ask if there would be more than one answer though, right?
Yeah, so you get 2 binomials as a result, so you would get back to these two. You're factoring 1 binomial into 2 binomials. It's one of the special ones.
What he's saying is that it could be -3x squared or positive 3x.
Yeah.
Sure, absolutely. That's a really good point, Ryan. I didn't even think about that. Yeah, great point. See what Ryan's mentioning? I know how we had a -3 here in front, oops, and a -3 here, and a -3 here. He's saying, well, if you factored this and try to factor it, you could write this as positive 3x squared and positive 3x squared, and you would still get this same exact answer. It's absolutely right. Good point. Really good point. Okay. All right, you have a few minutes, at least I think like 10 or 12 minutes, so give your homework a start for this section. Okay? It's done tonight, upload to Dropbox. I still want to see it. I have to go to the doctor tomorrow, so I'm going to be seeing her all day. So I have my phone, so I'm just going to check homework when I work on that at the office, just waiting. It's going to be like a 3-hour thing I have to go through. So please, make sure you do these both.